this. If someone could just give a thumbs up if the audio is coming through, I'd appreciate it. Alternatively, you could turn on your speakers and I'll know through audio cues if it's coming through. Okay. Sounds good. Okay. So last time we had, I had offered a sort of whirlwind introduction to monads as a conceptual structure, and I had noted some of the support for monads in Scala. Okay, today, reflecting the central role that monads will be playing within Spark, which is coming up within another lecture or two. I want to give a little bit of of additional coverage to this issue of monads. They're also one of the most interesting constructs within functional programming, one of the most powerful constructs, and one that really provides a highly viable and even favorable alternative for a lot of other programming language innovation, such as in the form of aspects, such as in the form of continuation handling in other cases, or they can form a way to handle continuations that can replace exception handling mechanisms, and in the form of certain design patterns that we'll see within the object-oriented space. So monads are very powerful construct. They allow us to extend our programs to collect additional sorts of information, to carry around sorts of information without having to go and modify the source of that source code from the ground up. And I motivated this last time with this notion of pipe and filter constructs, which are powerful ways of describing computations that involve typically multiple steps, and it does so. It describes those computations in ways that are quite concise, transparent, modifiable, and modular. And we've seen a number of examples like this where we have a series of computations built up. And in Spark, we'll be seeing quite a bit more. Not least because Spark actually reifies. It actually turns into an explicit object pipelines, particularly in Spark ML. Okay. I noted last time one of the challenges with pipelines is nonlinear flow of control. When we have exceptions, when we have cases that have to be handled in a special way, we have errors. We don't want our code to break needlessly, and particularly if you're dealing with massive amounts of data, this is all the more important because there may be all sorts of strange little things about that data, strange little patterns, cases where there's missing data, cases where the data falls into certain degenerate patterns. And we can't have our code operating on billions of records, in the course of a day, fail gratuitously, right? Even more so than that, to process these billions of records a day, to process these large amounts of data, we're going to be turning to resources that are quite large scale. This may be farms of machines, 1,000 machines at a time. And in those contexts, as others have well described, you can't treat machine failure or a node going down in the network or network congestion or other problems as an exception, as something that rarely handles and gets handled in an ad hoc way. You can't treat it as something that's a kind of just a diversion from your real job. It is your real job to robustly handle the coordination among large number of machines. And that means facing as a first order issue the fact that machines and networks fail, for example, disks fail. It's not an exception from our normal situation. It is our daily situation with large numbers of machines. And companies that maintain large farms of machines, such as Google, have long recognized this. And it's just a routine part of their operations that disks fail and machines fail. So when we're handling these nonlinear flow control for exceptional sort of patterns in the data, degeneracy in the data, missing values, or for errors in processing, we don't want to do so on a very ad hoc basis. We can't afford to do so in a way that treats these as minor issues. We have to treat it as a central issue. And one way to do this that is the focus of these lectures is monadic types or monads. Okay, and I noted that last time that crudely speaking, a monad consists of a packaged set of one or more values. Packaged in the sense that it's not just the value or values by themselves, but metadata about those values. Data that is collected in addition to the values. And I noted that this metadata in the simplest case, like the option monad that we've been dealing with, that data could just be, is there a value there or not? This is the maybe monad in Haskell, for example, that you'll see. There's maybe an int, or it may be nothing. It may not have a value, okay? Or it may be a value that says, or maybe a package which indicates, does this value, is this value in fact present? If not, what error happened, right? A try monad. It says there was an error of this sort. It occurred at this place. This is the exception that was originally thrown for it, and it provides the information about that. Alternatively, there may be a monad, that says where this value was computed, or from what data sources it depended on, or what coordinate system it's currently expressed, or what have you. Okay, these are all examples of metadata or paradata about the underlying values. And what's important is that as the computation takes place, it's computing the values, but it's also carrying along and supporting the computation of metadata. And what monads allow us to do is to take that same computation, that same basic pipeline, and carry around different sorts of metadata when we want to do so. So sometimes we might want to be interested in debugging this program. We want to know where a value was computed. Another time, we are trying to track down some aspects of provenance, what data is of high quality and what not, and we want to keep track of what databases this data was drawn. And maybe at most times, we're interested in having it robust to exceptions, and so we want to carry around any information about exceptions. And the beautiful thing with monads is we can kind of layer this information in there to be carried around with these values without going back and rewriting our whole pipeline, without extending our system in a very obscure way that obscures the underlying computation taking place, in a way that it makes it unwieldy. We can layer it all in a way that's a little bit reminiscent of what we do with aspects and aspect-oriented programming languages, where we kind of layer in aspects that are behind the scenes, that are invisible unless we want them to be, and that describe extra actions taking place. And in my view, monads provide a more robust, transparent, powerful, and frankly, beautiful way of capturing a lot of the functionality that aspects do. But aspect-oriented programming has many strengths, and I would recommend it for anyone who's interested in it. So monads is a sort of type that allows software developers to carry around this extra information. But it's more than that. It allows us to describe what sequencing means with respect to that information, to chain together sequences of steps, okay? With a monad, as we'll see, we're carrying around this information, but we're sequencing it in a certain way. So maybe what we're carrying around is a sequence of coordinate transformations that gave rise to this value. and we know the order in which they occurred. Or maybe what we're carrying around is a series of successive operations that are performed to calculate this value. Something will be very important in Spark, where we compute the lineage of a value, of a data set, not merely a value, but a whole data set. Remember, monads can have more than one value in them. And we do so to very powerful effect, namely that we can toss that away and recompute it at any time. We can toss away the particular values with the confidence, with the conviction, with the reassurance that we can recompute those. Okay. So there we need to keep track of the sequence of operations that took place to give rise to this. And in fact, in pure functional programming languages like Haskell, covered in 340, for example, for those who are interested, it turns out that there are ways of using monads to describe sequencing of things that you might otherwise think couldn't be easily described in a functional programming language. Things like things that perform I/O, operations that output things, send a message over a network, put something up on a screen, print out a message on a screen or what have you. You can use monads in a pure functional programming language to sequence things. And the key to it, what it comes down to, is those two operations that we talked about last time, which by which we create a monad from a normal value, and by which we sequence steps in a monad through Flatmap. What is implemented by Flatmap in Scala. Okay, so I noted there's many built-in monads in Scala standard libraries, and there's even more within the Spark context. And this is not just a Scala thing. It's a big issue in Java 8, although most programmers who work with them probably don't know about them as monads. It does secure mention, as I recall, in Kay Horstman's book on Java 8 for the impatient. Or is it Java 8 for the very impatient? I think it's for the very impatient. Monads are used in Java 8. I've mentioned other languages where they're used, and they form some of the most important contributions for achieving functionality that people often think is functional. Okay, so some have analogized these to programmable semicolons. It's almost as if each semicolon in a traditional Java program, or if you want to sprinkle them into your Scala, it's almost as each of those semicolons knew to compute extra things along the way. It knew to, keep track of what operations were performed on the value, calculated in the statement, or where these values originated within the program, or what have you. So these programmable semicolons, it's like we can take those semicolons already in our program and we can weave in extra logic, okay? So I've noted they can allow for handling convenient composition of functions while evolving and maintaining and accumulating and processing additional information along the way. And it allows for this clean handling of alternative control flow, which is so important in the big data context, but also accumulating information like lineages, which allow us to be sipping and to only take small amounts of memory. And in fact, enable things like streams, which do similarly. They allow us to minimize our memory footprint, okay? So monads are central in their stream form and allowing for laziness. Remember laziness? Why do I say laziness can be thought of in a monadic way? Why do I say that? Think about streams. What metadata is a stream keeping other than the values in the stream? How to compute it. Yeah, it has to. I mean, that's what one of the delights of streams, right? You could pass them around, and you don't have to pass a lot of extra code with it and descriptions of what to do with it and how to calculate more. It knows how to calculate more. It brings that along with it, along with the values that happen to have computed thus far, and it knows how to compute more. So that's an example of a monad too. That's a very powerful monad. Futures is another one. We know how to compute. This value isn't computed yet, but it will be computed. And we know what to do with it once it's computed. Okay. So they can simplify and clean up code. Now, monads do provide these ways of accomplishing things which programmers pursue in other ways, like inversion of control with dependency injection, etc. Callback mechanisms. I know some of you, such as Dorian, have taken operating systems classes, and if you've done operating systems before, whether it's in an exception table or other or I/O or what have you, you'll recognize that there's often a need for what are called callback mechanisms. What do we mean by callback?
Like event handling?
Yeah, okay. So that can be done very much with the callback. So what's the idea behind a callback? Okay, yes, we could do it with the future, absolutely. And in fact, that's a more beautiful way to do it yet. But, with a traditional callback mechanism, basically, you might specify, hey, tell me when you're done with this, right? Or tell me when this happens. And you pass it, well, in classic C, you say a pointer to a function, right? Or you pass it a reference to a method in C++, a pointer to a method or what have you. And you say, hey, give me a call with this method when you're done. And a lot of functionality in operating systems can be accomplished with that. Did I say exception handlers before? Interrupt handlers. Interrupt handlers, ladies and gentlemen. One of my formative experiences when I was still in high school was frobbing interrupt handlers in assembly language and making interesting things happen on an original IBM PC. That was fun. And interrupt handlers are one of these mechanisms by when an operating system experiences an event of significance. Maybe it's a key press. It will call off to your event handler. Well, it's an event handler. It's an interrupt handler to handle that. Right? And there's a table of these interrupt handlers, which is stored, and it will call the appropriate one when the appropriate action happens, right? And it's a callback mechanism. And it turns out we can handle that much more nicely in a self-contained way with futures, which I'm hoping to cover either next time or the subsequent time. Okay, so what do these monads look like? By the way, you may wonder, why am I talking through this again? Monads are a notoriously slippery concept, okay? And there's a famous, well, okay, maybe it's not famous. It's not on TV or something, but it's a cartoon which shows two people laying on the grass looking up at the clouds, and one of them says something about monads. And the other, maybe someone can find it here. The other, and they say, every time I think about monads, I think I understand it. And then I think about it later and I decide I don't really understand it. And monads are a little bit like that. So I'm trying to reinforce this intuition rather than leaving them fluffy and sort of distant. I'm trying to reinforce the operation, this notion of them as a concrete sort of set of properties and it's offering certain value. There are certain parts of it which will be slippery, but hopefully you can understand some of these basics. So what are some of the basics we talked about last time? Well, okay, monad is commonly type parameterized in something like Scala, right? It's a monad of something, right? So it's an option of int. or it's a trie that can hold a double, right? It's a stream of characters or strings, right? So it's commonly a type parameterized construct. The type describes what are the types of the values in it. And there's two key operations that allow it to be handled in a monadic way. One, and both of them are described by unusual names. Unusual and sort of confusing and ambiguous, unfortunately. The first is this one commonly called unit or return or pure, and basically it maps a value into that monad. So give me an example of something that does this in Scala. Okay, don't look at that. don't look at this. So what's something that does that that's not listed there? Yeah, okay, none. I think it's none. None. Yeah, so give me my Scala here. Okay, so here we go, and it's going to be val O1 equals sum of 3, right? This is is that applying this? Is that applying this? Yeah, it is. Sum takes a value, it, in this case 3, and maps it to a monad, right? There it is. It stands before us. Okay. The other thing you could say is, okay, I'm going to make this explicit just so you could see very closely that this is none here. And then I could say O1, O2 dot, and this is going to bring us to a second operation. If I want to perform an operation that involves these two, if I want to say here, and I'll put in another one, sum of 4, okay? Okay, so suppose I want to add together two of these. How would I do it? Suppose I want to add together O1 and O3. What would I do? Suppose I want to create a monad that reflects the addition of those two. Suppose I want to lift plus to the monadic domain. So we have sort of an equivalent to plus among monads. Give me a formula that would give me a monad that's the sum that represents the sum of O1 and O3, speaking informally. How would I add those together?
You use map on
okay. Yeah, so in this case, I could do O1 dot speak on. Sorry. Okay, now map will be part of it, but what do I have to start with? I need to start with a flat map. And that's the other big operation here in Scala. It's this bind operation. It's going to take in a monad. This is actually what we're going to call it on. The value on which we invoke this method. And this is going to be a what? What is this thing? It's a function. It's a function that takes in a normal value and it returns a monad. And the whole thing is going to return back a monad. So let's go see that, right? Okay, O2 dot flat map. Okay, and then what is it going to take as a function? Okay, what does this function take in? It takes in yeah, it's the element of O1. It's a value. It's a particular value of the concrete domain. In this case, it's an integer. So we'll call it. Shall we call it I1? I for integer. What do you think? Okay, we could do worse. Okay, so what does this function need to do? So what is this I1? It's the int that's inside of what? Of O1. Okay, now when we get that int, what do we need to do with it? Well, short of before we convert to monad, we need to add it to the other one. How are we going to do that? Okay, so we got our int. Got our int from O1. Now we want our int from O3. What are we going to do? Sorry? Yeah. Okay. Good job. Okay. O3 dot map. And we will do what here? Okay, so this is a map. What does map take in? It takes in a function. And what is that function gonna, what's that function gonna take in as an argument? It's a function that takes in, yeah, it takes in an integer here. And what's that integer? It's the integer that's inside of what? Oh, 3. And then what's it going to return, this function? We're at the cusp of greatness. What is it going to take in? Sorry? I1 plus I2. Boom. There it is, right? Okay. This is the sum of that. Okay, now let's suppose I'm going to add. Well, okay, so suppose I did O2. What's going to happen there? We're going to get back none. Why are we going to get none? Yeah, because we're going to call Flatmap on none, and it says, oh, this is nothing. There ain't nothing here. It's empty, right? And so it can just return what? None, yeah. Boom. Now suppose we were to instead have this. What would happen? Is this gonna die a horrible death? No. What's gonna happen?
None.
Okay, why is it gonna be none? So let's trace through. With this case, when O2 was none, did this function ever get called?
No.
Never got called. It was short-circuited. Never got called at all, right? It just said, hey, this is not, I don't need to do this computation. Cut it short. Okay, here, is this function ever going to be called? Yeah, but what happens when it gets called? So it's going to get in an I1, which is going to hold the value in O1, right? Which is 3, I think. Yeah. And then what's going to happen? It gets its 3, and then what's it going to do? It's going to call O2.map. And what is O2.map going to do? It's just going to, return none. Because it knows it's being invoked. Map is being invoked on something that is none, right? And so that's going to return, this whole thing is going to return none, right? And because this is a flat map, what is that going to yield? It's going to yield none for the result because it flattened. And it's not going to yield some of none. It's going to yield none. See that? Okay. Okay, now, so this is Flatmap, and Flatmap serves as this bind operation, and it allows us to take a monad value and then a function to apply to the value of the monad, and it returns a resulting monad. Okay, and the second argument here, in contrast to map, for Flatmap, the second argument. Excuse me, this argument, I said second, but really it's in this context, it's the first, the function passed in. Let me just say that because that's a little bit confusing about whether it's a method or what have you. The function passed in is a function that takes in A rather than a monad of A, and it returns, the function that gets passed in returns a monad, right? Okay, now, let me ask this. Why isn't this a flat map? Why isn't that flat map? Yeah, this is computing. Is this computing a monad? Remember with flat map, with Flatmap, it returns, the function it passes in returns a what? A monad. Is this, whoop. Sorry, folks, okay. Is this returning a monad? What is it returning? a concrete value, ladies and gentlemen. So this is map. Do you see that? Okay, now let me sweeten this. Okay, I don't know if it's sweetening the pot. Let me let the plot thicken more. Okay, watch this. Val 04 equals sum of. Okay, you see that? Okay, now. Suppose I wanted to add together 01, 03, and 04. What expression would I write to add those three together? Ah, it's exactly right. It's exactly right. Okay, so two flat maps and then a map, right? Okay, so help me write it out. So we're going to have something like this. We're going to have 03 dot flat map, and then that's going to take in a what? I2, right? And then what are we going to do with that I2? Suppose we're adding I01, 03, and 04. What are we going to do next? 04 dot map. And what is this going to be? I3, and we're going to add them together. You see that? Uh-huh. And then I think I need another paren. Yeah. Right? Okay. Okay. If I had to do interesting brain imaging experiments, one of them I might do is take software developers and particularly Lisp programmers as a key example and see what parts of their brain light up when they're matching parentheses. Like a whole like part of you that's like, okay, is a curly there? There's a square bracket and a parenthesis. And with Lisp, it's just like parentheses all the way down. Yeah. Okay. So, ladies and gentlemen, there we go. And you see the pattern here. Why two flat maps? Why isn't it a flat map and then a map and a map? Because what can happen with this one? Why does that have to be a flat map? It returns a monad. Why does it have to return a monad? Yeah, and actually, so I'm going to refine that. It takes a function that returns a monad, right? That's the key thing, because like if you call map on a monad, right? What does it return? Yeah, it returns a monad. So if I call here, I mean, just to illustrate this, just to be clear about terminology here, and I think this is what Nell was referring to. If I were to take map and I were to say I1 plus, let's do this, right? What does this return? 01 is a monad, right? It's an option. So what does this return? It returns a. Sorry. Yeah. It's a sum. It's a sum of 9, right here. And this is the point. Is this is a monad here. So both flat map and map, the return value of it is monad. But the key differentiator to which Nell referred, I think, was the fact that a flat map takes in a function that returns what? Map takes in a function that returns a concrete value. In this case, it's an int, right? Flat map takes in a function that returns a what? A monad, ladies and gentlemen, a monad. Map and Flatmap both return monads. The difference is that Flatmap takes in a function that returns a monad, and this one takes in a function that returns the concrete value. Eh? In the book, in the chapter on try and option and so on, the author mentions that he said he used Flatmap, thinking about like cases where you're using try, for example. You use Flatmap when the operation that you're performing on the elements of the monad you're calling it on, so like O1 dot, and you're choosing Flatmap or map based on something you want to do. If that thing you want to do to the elements of O1, or the things you want to do to the elements of the stream or to the elements of the vector, if it can itself fail, then you want to use Flatmap because you want to return a try. By contrast, if what you're doing can't fail, like here, is this going to fail? No. So we use map. By contrast, could this thing fail? In other words, could it return a none?
Yes.
Yes, it could. If what were none? 04 were none, this could return a none, right? And not return a non, but return a none. And ladies and gentlemen, that means that Flatmap has to be invoked with you want to use Flatmap here, okay? Because it can itself fail, right? We're not just returning a concrete value. What would happen, just for amuse me, if I did map, what would happen here? Yeah, that's not what we want. The thing inside of here can fail. It's returning a monad. So we need a Flatmap here to flatten it, right? So ladies and gentlemen, we have this pattern that we have Flatmap, 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 however deep it goes, except the last one. If this isn't going to fail, we want a map. Okay, now, forgive me, but we're going to import Scala .util.underbar. Boom. And we're going to create corresponding tries. Is that okay? So I'm just going to illustrate something. Val T1 equals try of 3. Forgive me, I'm not being very creative this morning. T2 is this. This is a failure. Val T3. Do you recognize where these values are coming from? T3 is what? Try of 4. T4 is try of what? Okay, these are just the corresponding ones. I actually could have said, I could have alternatively just said this. O1.2 try, probably. Oh, no, it's not. Okay. But it didn't do it. Okay, so I just created the corresponding ones, okay? Now watch this. We're just going to adapt our pipeline here, okay? Could we do this? Instead of where we have O, we'll just put the T for that. Could we do that? Cannot.
You can.
Cannot. Yeah. See that? Okay, wait a minute. This is the defective one. This is the defective one. Okay, there we go. Works great, right? Okay, now, suppose that we were to have one of these guys. Suppose we were to have a operation that can fail here. Imagine that. Let's engineer an operation that can fail. Are we okay with that? Okay. So I'm going to divide I3 by, sorry, I2 by I3 minus 1. Okay. If this thing, could this thing fail? This thing, well, under what condition could it fail if I3 were 1? And is it possible that I3 could be 1? What is T3 after all? Oh, sorry. What is T4? Sorry. If so, I3 is okay. This is a bit confusing. I3 came from T4. Okay. Okay. So, I lost it. Oh man. Okay, I lost it along with the extra parens. Okay. Here we go. Boom. There we go. And there we go. Okay. Oops. Invalid literal number. Okay. Sorry. Don't. There we go. Okay. So, yeah. Mumble. Okay, what is it? Okay, this is a most curious situation. Okay, let me engage in debugging behavior. So this is 6. I was expecting it. Oh, what have I forgotten? Yes, it's parentheses. Sorry, folks. Of course, rookie mistake. There we go. So that part of my brain is, I guess, withering or something. Okay, so ladies and gentlemen, divide by 0. Do you see this? Now, the interesting thing here is that this is indeed nicely mapped, right? And to try, right? What would happen if we did a flat map here? If we did a flat map, then it's going to be complaining that is not a proper operation. What would we need to do to make it happy? Wrap in a try, exactly. Wrap in a try. Boom, boom. Okay, there. This would also be an acceptable solution. So this is an example of something that can fail. So we use Flatmap, and it's returning a monad, right? The function that's passed to Flatmap returns a monad. The function that's passed to map does not return a monad in general, right? It's a non-monadic construct. It's just a concrete value. Okay. Okay. Now, this is something I did want to cover, and we're sort of triaging some things here. I want to cover some special syntax in Scala because, amongst other things, it can be used in Spark, and because it's exactly designed to deal with this sort of situation. It turns out that Scala, like Haskell, provides special syntax for monads to support monads in monadic computations. Okay. So the syntax is like this. You have a for, you use these little left arrows, and you have a yield. Okay. Something like this. So here we have try values created, and we can just add them together like this. Okay. And it provides us a way to capture the same functionality we've just been exploring, but with less syntactic cruft, because we don't have to write out Flatmap and this passing these successive arguments. That's all actually implied by this, and we'll get to that, okay? Okay, so here we go. Let's try applying it to our case. We're going to do a for just like this. So I'm going to say, okay, so you don't have to do this, but in my impoverished world, I'm gonna do it. I'm gonna say for, and I'm going to say v1 gets t1. T1. V2 gets T3. V3 gets, you know what, I should have called it I3, I1, I2, I3 to be completely analogous. Maybe we'll do that in just a minute. And I could say yield V1 plus V2 plus V3. Okay? There we are. Okay. So here I'm performing an operation on these concrete values. Let me, just to sort of make it clearer, I'll rephrase it using the original variable names. I1 gets T1. I2 gets T3. I3, I'm just rewriting it with I's, okay, in my crude textual way. I1 plus I2 plus I3. You see that? Okay. So this is precisely the same as this guy here, as the correct version of that, this guy here. It's precisely the same thing. This is syntactic sugar, as we say, for this, okay? This provides us a crisper way to write it. It provides us a way to characterize a long sequence where we're basically operating on things monadically and performing flat maps where these things can fail. We can write it using this for syntax. So this desugars into a nested series of calls to Flatmap, where each of these guys, like x1, is bound to the concrete values in the monad, and it's performing a final map to around the yield expression as the value of the entire thing. Okay. Now, it turns out you could do much more than that. In Scala, you can also write if here. And basically that will desugar into what's called a WidthFilter call. Okay. So imagine if you had a long vector of millions of elements and you wanted to extract, for example, from the vector things that are greater than or equal to 0, or things that are not nan, or what have you. We could do so, and basically it will yield, you know, a vector of those things that are greater than 0 by an equivalent thing like this. Now, what's powerful here, I don't have time to go into it in detail, but what's powerful is that WidthFilter is a little bit different than filter. Where have we seen filter before? Do you remember filter? Remember filter? Whence did we see that before? Where did we see that before? Where before did we see it before? Yeah, okay. Okay, indeed. Just to remind people, right? We had a vector 1, 3, 5, 7. Let's make it start with 2. And 11 here, right? There we go, right? And we could do vec1 dot filter. And what does filter take as an argument? A function. Indeed, it returns a Boolean, right? So we could say if this thing mod 2 equals 0, right? And what will we get back here? Okay, but more precisely, it'll be 2 wrapped up in what sort of monad? In a vector. In a vector, right? Yeah. And that's what WidthFilter does as well. But what's cool about WidthFilter, and I don't prove that here, but can you actually directly invoke it? Yes, there we go. What it actually returns is a traversable structure that allows you basically to avoid recreating a structure of this. Instead, it just references which of these original elements are that. So you don't have to create new data structure. It just points back to the references which passed. The references in the original data structure which passed the test, which passed the filter. So it's particularly memory sipping. It allows you to basically avoid creating a whole new data structure of vectors here. And to just refer back to the particular elements earlier that match this criteria, okay? Now, you may wonder, well, wait a minute, I thought streams only do things incrementally. Yeah, streams are a different matter. But for vectors, if I fill a vector with 100,000 elements, random numbers, and I filter it to only include those that are, equal to, I'm tempted to do it. Thou vec2 equals vector dot fill, right? Remember that? Take it with 10,000. I won't tempt fate here, right? Oh, we need rand. We need a random import Scala dot random. Is that right, or is it capital? Mumble. Scala dot. Oh no, it's not. Util dot random. Is that util dot random? Scala dot util dot random. Thank you. Humble. Okay. Happy. Okay. And so then if I did val vec2 equals vector dot fill of 10,000, and I did next int, right? There we go. 10,000, right? And now if I did val vec3 equals vec2 dot filter, this thing to look for things which are even, I would get back a whole new collection, right? There's a whole new collection. Boom. It's a pretty heavyweight thing. It's of size somewhere around 5,000. Yeah. Okay. But if I were to do vec4 dot WidthFilter, how big is that? So it turns out it's filter monadic, you notice here. But it turns out that it's of a certain size, but it actually is not reified in itself. It's actually just pointing back to the elements of vec2 that are where this is true. So it doesn't have to create it anew. It's a traversable-like type structure. Okay. Which is useful. Okay. So Scala provides this extra support for monads and for work with monads with its for syntax. Now, a lot of the place that you'll see this in Scala is, not surprisingly, with collections. You'll see this with vectors, or you'll see it with streams, or you'll see it with arrays, or what have you. And that's fine. But a lot of people who use it, perhaps most people who use it, don't realize that behind the scenes, this is a general monadic operation, and it is fruitful to use when you are dealing with monads in general, so that you can have crisp syntax that describes what you're doing without the clutter of very, very long sequences of flat maps and maps, right? It allows you to sort of crisply express what you're doing without a lot of additional syntax, okay? You can use that in the Spark context, and we'll see if we can weave that in to some examples there, okay? So enabling monads in a clean, crisp way. The beauty of this, you may wonder, well, why would we do that? Well, again, the whole point, a whole key point here is that this syntax and this one, the syntactic sugar for it, they provide a way of carrying along with this computation like this, carrying around a lot of other information. We can perform the computation as if we don't have to worry, using the syntax, as if we don't have to worry about the extra information being carried along. But this is carrying along the extra information for this to be a try, right? It could be carrying along the extra information involving coordinate transformations, involving provenance of values, involving where in the program values were computed, etc. And we would just have to focus on the actual computation as it involves values, but it would carry around the other stuff essentially for free. It carries around the other computation elements of the computation, and with lighter weight syntax than we get here, which is where we're also carrying it around. Okay? It's a little bit more in your face with flat maps, etc. It's a little bit more obvious. Hey, there's some extra stuff that could be carried around here, whereas this makes it a little bit more crisp. Okay, those are some examples of that. You know, to have an example of this that's maybe a little bit more routine. We might have a case where we have a string which points to our URL, and we're going to here want to return something that finds the first string or not in a page. Why don't we go and do this one rather than talk it through? I would suggest that we actually pursue this one. We only have time for a few of these, but we could pursue this. So okay, okay. So this is going to be find smoking and page at URL. It's going to take in a URL, and it's performing some monadic operations here. Okay. And you'll notice critically, it's using a try here. It's converting it to an option for reasons we'll talk about. And it's trying to find a matching string and return it. Okay, so let's go do this. Okay, here we go. So I'm going to put it into this. Okay, and I'm going to say def find string in page. And I think I call it str URL. Here, come on. Str URL. When I was your people's age, I was pretty good at naming things. And so I could write a lot of code, and with about 80% probability, I'd know how I would name something. And so I could really easily search for it and so on, because I knew, like, okay, if I had something like that, I'd name it like that. And it was quite useful at times, particularly in the era before IDEs or when they were just starting to come in. Okay, so here we are. This is something that returns a value. So what do I need? This def. So I need a what? it returns a value, so I need a equal sign. If it were just a procedure, it was just something that subroutine that undertook an action, I don't need an equals. It's just doing something. It's not returning a value. But since it returns a value, I need an equal sign. Eh? Okay, here we go. Okay. Okay, so we're going to need, oh, I don't even need to ignore my little curlies there. I'm stuck in a situation where I'm imagining curlies as being needed. Okay, so here we go. So we want a 4. And the first thing we want to do is we want to get an option here. Now, a key thing here is all of these have to be the same basic monad. So they have to be like option of something, okay? Or try of something. They all have to be tries, or they all have to be options, okay? This is one of the limitations that we have here, okay? So there we are. We're going to have URL here. Call it URL. And it's going to be sum of str URL, okay? That's because it has to be an option. Okay, there we go. And next, we are going to get the page context. And the key thing here is we're going to get the contents of this URL over the web. And we're going to render it into a string, okay? Then we're going to turn it into an option here, okay? So here we go, str page contents, that's, and we're going to have a try, source dot from, and I think it's with capitals there, from URL. This is actually something where a couple seconds of delay with the live video feed may actually be to your advantage, because it's still showing on the live video feed even after it's gone from there. It's kind of a neat hack if you can take advantage of that. Okay, so we're going to have this, and then we're going to do dot, I think it's called mook string, which is, in my mind, a sort of displeasurable name, but they didn't ask me. Okay, and then I say to option. Okay. See that? And make sure I got the from URL. Make sure I got that right. Yeah. Okay. So this is trying to do this. What could go wrong here? What could go wrong? Why do I need a try around the from URL.make string? What could go wrong? Accessing a site over the web. Yeah, it's not found, right? The page at that URL is absent, right? Could that happen? yeah, you bet it could happen. Okay. Okay. Next, what do we want? Next, we want to do matching strings. So here we are going to use Scala regular expressions. Now, it's one of my regrets of this course. So we haven't had a chance to really poke around with Scala regular expressions because they are great and they're beautiful and they use monads in terms of option. But they also use unapply in a really nice way where you can just match things and very easily get the matches and so on using the unapply operator behind the scenes. So this is what we want. Matching string gets this, okay? And we're going to be looking for the matching string smoking in there. These triple quotes, what are those for? It's a what string? Begins with R, ends with W, has an A in the middle. Yeah. So this is a raw string, okay? There's 3 types of strings in Scala. Again, regular strings, which allow for like \n to be a new line. There's raw strings where if you put \n, it's \n. And then there are substitute strings, which allow for so-called interpolation. So if you have $, the name of some variable or value, it'll substitute in the value. And you can actually perform a little computation in curlies. Okay, this is a raw string. See that? And then .r turns it into regular expression. Find first in is going to find the first occurrence of that string in these page contents. But it may not find a value, right? Why might it not find a value? Give me 2 scenarios where it might not find a value here. What's one scenario it might not find a value here?
Page doesn't contain the search terms.
Yeah, the page doesn't contain the search terms. The page is valid, but it doesn't contain the search terms. Give me another reason it might not return a nice value there. Sorry? Yeah, the page doesn't exist, right? So ladies and gentlemen, there's several reasons that, and that's the whole point. I mean, options, try, these things can handle not just one occurrence of a failure, but multiple along the way, right? And there's different ways things could fail. That machine could fail, that one can fail. You know, the machine is not updated with the latest API, etc. So we want to be robust under all these different combinations of things. And the final thing is we'll yield the matching string here. Okay, here we go. And there we go, and yield, and we'll say matching string. Do I need friends? I don't remember if I need friends. They don't hurt if we don't need them, but boom. Okay. Here we go. Boom. Oh, source. Import Scala.io. Boom. Okay. Import Scala.io for the future. Okay, here we go. Forgive me, I'm going to copy it directly. And paste, right? Boom, boom. Okay, so there we are. Okay, find smoking in page at URL. Okay, that's a little bit more wordy. Okay, so I'm going to try to find this in HTTP usas.ca. What do you think I'll get? None. What if I try to do it in foobar bazap? None. Okay, just to be sure, because someone might have registered that. They're so canonical. Okay, ladies and gentlemen, suppose I were to do it instead in this URL here. Okay, I'm going to copy it, and I'm going to paste it in. Okay. Let's choose underbar initiative. Okay. And there we are. Okay. It found it. Okay. So what we've seen here is situations where we could have multiple routes of not finding it. One is the site doesn't exist. Another is the site exists, but it can't find it. Yet another possibility, of course, is that it does exist and it could find it. Okay, just to sort of do this more, let's just see for a regular expression how that's found. So if I were to do this dot find, okay, first in, and I were to do, I don't know, bar foo or something, something like that, you notice it found it. You notice what find first in returns. It returns a what? What does it return? Does it return a string? No, it returns an option of string, indicating if it doesn't find it, what do you think it returns? None, right? And this is very common in Scala libraries, and it's quite common in the Spark libraries as well. There's a lot of operations there that are returning option to indicate, you know, they didn't find anything or what have you. Okay, so keep an eye out for that. Now this is using for syntax, and because of that, we don't have to paste together a dot flatmap dot flatmap dot flatmap dot map to wrap up all of this. Instead, we're operating in terms of what? What is this thing here? It's a what? Well, okay, but what sort of type is this? It's a monad. And what sort of monad is it? It's a option. Good. Okay, what is this? It's an what is option? It turns it into an option. What is this? What did we just see? What is find first in return option? So these are all options, and indeed they all have to be the same type of monad. But what is URL? What is that? It's begins with a S. It's a string. What is str page contents? It's a string. What is matching string? It's a string, ladies and gentlemen. And yet, it's doing all of this and bringing along the option value information. So if any of these fail, like if this guy fails, is this guy executed? No. If this guy yields a none, then this one is not even executed. It's just like with Flatmap, right? And if this one, you know, fails, it's going to return a none as well. So, ladies and gentlemen, what for gives us is the ability to compute with things as if they are values. The ability to sort of frame things as if they are values, but at the same time have the robustness of bringing along all the monadic sort of operations. Do you see that? Same thing with this, right? We can A, B, and C here are ints, and we can compute in terms of them. But if any of them fail, this will automatically be short-circuited. And if this thing fails, it will also return a try, okay? Which is, in this case, a failure if this thing fails. So we kind of almost get the best of both worlds, where it's as if syntactically we're operating in terms of the actual values within the monad, but it's as if in terms of the robustness and bringing along the monadic values and so on, we're operating with all the monadic context. Does that make sense? Yeah. So that's what the for gives us. And I give a bunch of examples here of this sort of items. And I use that to explain, this is actually a different one, which I should post here. But this is about chapter 6, okay? And I give a set of additional examples here in terms of how they operate, and trying to explicate some of the examples in the book with greater clarity as to what's going on, like with this int and ints and that sort of that sort of thing. Okay. Okay. So that's all we have time for today. I hope this has reinforced some understanding about what these monads are, how they can be combined, and how they can be denoted in a crisp, compact syntax using Scala's for construct. And these sort of monads will be looming large behind the scenes with our use of Spark, okay? And we will see them likely later on in a little bit more detail with futures, which are a powerful way of wrapping up promises of computations within Scala, and which have analogs in Java 8 in the form of computable futures. These things called computable futures in the Java 8 libraries, okay? But my interest is in getting pretty quickly, although at a didactic level, it might be nice to cover a few more types of monads like futures. My interest is in getting you up to speed with at least a few basics of Spark before the break. So next time, well, it goes against some of my pedagogic sort of impulses. We're going to be going into Spark, okay? And the construct that I've been using thus far for most of the lectures has been this Scala shell, but I'm hoping that you've been following along on Zeppelin, because next time I will be Zeppelizing my lecture, okay? I'll be using Zeppelin, and we will be using specifically the fact that Zeppelin supports Spark in addition to Scala. And I'll be walking you through some basics with Scala and Spark, and with use of Spark for some basic operations using Scala as Spark's native language and to accomplish some basic operations, okay? So that's for next time, and that's with an eye towards giving you some sort of legs up on the key technologies that will be of relevance for projects, okay? Thank you very much, ladies and gentlemen. For those who are interested, I heard a delightful rumor which proved true. So one of the lab members apparently, I wouldn't have believed this, but it's true. One of the lab members ordered shirts that profess a love for functional programming. It says, "I love Lambda," and Lambda is the it refers to lambda calculus, which is how we denote functions in lambda calculus, but how you can create closures. Okay, so she ordered T-shirts and I think a book bag or something that state to the public the love of functional programming, and then she proceeded to show me a site which was chock-a-block full of similar tchotchkes, like similar types of things that you could get. So I'm trying to figure out how to use it, but you may see me with a different dress code in some some future lecture. Yeah, it's quite a sight. So if you get a chance to ask, Chin Yang is the person to whom I referred, and I think she showed it to Yuan.
She also bought me a bag that showed iLambda functional programming.
So I admire good taste, and I think that's awesome. So I will tell you, folks, that I used to so at MIT they actually have quite a few tchotchkes related to this, and one of them has sort of a recursive lambda expression, and it's actually, I think it's the Y operator, and it shows it on a little button. And I used to have one of those, but the other one I had was a nerd pride button. And during my opening years here, I would sometimes wear this nerd pride button. But then there was another professor who was, well, he also shared tendencies with me. And so he had a retirement, and I had to give it to him as part of his retirement. So now I no longer have it. But now this is a good supply. So I appreciate Jin Young's. I think she was inspired by 340. Yeah, to get it, which is great. And so I'll see if I could let people know about this site. I have no financial involvement with this. Yeah, anyway, thank you very much. Take care there. Give me just a second to stop the recording. Okay, stop sharing and stop. It's still recording me. Here we go. There we are. Okay.